Hello everyone. In this video, I'll be walking you through our project titled Hybrid Multimodal Feature Engineering Frameworks for Phenomena Detections. Our goal is to combine chest X-ray image features and lung sound audio features into one unified system that supports better and earlier phenomena diagnosis. Phenomena continues to be one of the most major cause of respiratory hospitalizations. Doctors typically rely on two clues, what they see in an X-ray and what they hear through occultation. But relying only one modality can miss early or subtle cases. This motivated us to build a system that uses both sound and image information just like clinicians do. Let me take you to the feature engineering overview. In this project, we extract handcrafted, clinically interpretable features instead of relying fully on black box deep learning. For chest X-ray, we extract texture features like GLCM contrast and entropy, shape descriptions like HU moments, and also intensity and edge-based features that helps highlights, opacity, and infiltrates. For lung sounds, we compute MFCCs and spectral entropy, zero crossing rate, RMS energy. These features helps detect abnormalities such as wheezes, crackles, and airflow turbulences that are linked to the phenomena. Let me take you to the multimodal fusions like CCA. Once both sets of features are extracted, we fuse them using the canonical correlation analysis or CCA. CCA maps images and audio features into a shade space where the relationships are maximized. This allows the model to learn patterns like high X-ray opacity, high spectral entropy, often corresponded to the phenomena. These synergies provides more reliable diagnosis predictions that uses images only or audio only approaches. Let me tell you the visualizations and results. We used confusion matrix features, distribution plots, and comparative accuracies charts to evaluate or model. The multimodal system consistently shows high accuracy, fewer false negatives, and better class separations compared to the unimodal. Let me take you to the ethical frameworks. Because this is a medical AI system, ethics plays a central role. We follow the principalism frameworks, which includes beneficence, that is, maximizes the patient's benefits, non-maleficence, avoiding harms through the transparencies, justice ensures the fairness across the patient's groups, and also anatomy giving clinicians interpretable informations they can trust. Our feature engineering approaches supports all four pillars by keeping the system explainable, equitable, and also clinically meaningful. From here, my friends will continue and walk you through the coding and implementation part.
Hello everyone, my name is Syed Furkhan Hussain and we are from Group 15 and our project is Hybrid Multimodal Feature Engineering Framework for Pneumonia Detection. This project focuses on detecting pneumonia from chest X-ray images and lung sounds using feature engineering. My role in the project was to handle the entire image processing pipeline, including pre-processing and feature extraction. So instead of using deep learning or CNNs, I manually extract meaningful features from each X-ray image, such as texture features, shape features, intensity, edge densities, and a custom feature as well. All these features are combined into a single fused feature vector and then used to train a machine learning model. The goal of the project is to build an accurate and fully interpretable pneumonia detection system. So begin with, first I mounted my Google Drive so I could access the dataset stored in my Colab drive. Then I unzipped the chest X-ray dataset into the Colab environment. Uh, Moving on, the dataset which I used is a chest X-ray pneumonia dataset, which contains two categories of images. One is for normal and one is for pneumonia-infected lungs. So these images are taken from real clinical settings and are grayscale X-rays of patients. Next, I imported all the required libraries for image processing, feature extraction, model training, and visualization. So begin with, before extracting any features, I pre-process every X-ray image by resizing it, converting it to grayscale, removing noise using smoothing filters, and applying histogram equalization to improve contrast. Then I extract texture features using GLCM for global texture, LBP for micro texture, and a custom feature called UTSI, which combines texture strength, entropy, and intensity into one score. After that, I also compute shape features like hue moments for geometry, Canny and Sobel edge densities, mean and variance of intensity, and pneumonia affects both texture and shape. So combining both helps improve accuracy. So all the texture and shape features are combined into one single vector per image. I run this function separately for normal and pneumonia folders. Finally, I merge everything into one dataset and save it as a CSV file in the drive. This cell extracts fused features, texture-only features, and shape-only features from both classes and save them as CSV files for training and analysis. Then I split the fused dataset into training and testing sets and then train an XGBoost classifier. XGBoost works very well with engineered features. I evaluate the model using accuracy classification and confusion metrics. So my model achieved an overall accuracy of 91%, which is quite strong considering this is a feature engineering based approach, not a deep learning. So out of normal images, 227 were correctly identified and 43 were mistakenly labeled as pneumonia. For pneumonia images, 730 were correctly detected, while only 47 were misclassified as normal. So for new X-ray images, I created a prediction function that extracts the same features, runs the model, displays the X-ray image, and prints a full explanation of features that influence the decision. So let us try with one simple X-ray. So let us test our model from the Google images. This is the image which I took from the Google, and it is a normal lung X-ray. So as you guys can see, it predicted as a normal lung. Now moving on, we'll call the same function for a pneumonia image. And as you can see, it predicted correctly as a pneumonia. And we'll try it with some other image as well. Here, it predicted correctly as pneumonia detected. Yeah, moving on to the audio features.
Hello, this is Dyuti Shri, and I'll be walking you through the audio part of our project and how we connected it with the X-ray data using the canonical correlation analysis. So we've started with the raw lung sound recordings, which were often noisy and inconsistent. To make them usable, we cleaned the signals by applying the bandpass filter that keeps only the medically relevant frequencies, removing the silence in the audio and also by reducing the background noise. This gave us a clear audio that focused on actual breathing patterns like crackles and wheezes, which are the key indicators of pneumonia. And once these signals were cleaned, we extracted a variety of features that describe the sound using Librosa. We computed MFCCs to represent the tone and texture of breathing, along with the spectral and time domain features like bandwidth, centroid, RMS energy, and zero crossing rate. Together, these capture how airflow behaves inside the lungs, basically, how rough or smooth the breath sounds are. Next, after preparing the audio features, we brought in the canonical correlation analysis, which is the CCA, to link with the audio and image features extracted from the chest x-rays. The idea behind the CCA is simple. It basically finds the patterns that are shared across both types of data, which are the sounds and the visuals, and projects them into a common space. So here is a graphical representation. The x-axis shows the image projections and the y-axis shows the audio projections. Blue points are the normal cases and red ones are the pneumonia cases. So we see there's a clustered together along this diagonal line. That means that the CCA successfully identified a strong correlation between what we hear in the lungs and what we see in the X-ray. Then finally, we used these fused features to train the models like SVM, random forest, and logistic regression. As we can see here, the model which has achieved the best performance is a random forest with 66% accuracy and AOC over 0.82.
So, this is Mallikarjun Kotta. So now I'm explaining the remaining sections of our project, starting with our personal position. We believe that multimodal feature engineering approach is far more effective and clinically reliable than either using X-ray images or lung sounds alone. X-ray shows structural abnormalities like opacities, while lung sounds captures functional issues such as wheezes or cracks. By combining these two complementary types of information and aligning them with canonical correlation analysis, we get a much richer and more meaningful representation of pneumonia. A major advantage of our approach is interpretive features like GLCM texture or MFCCs directly related to clinical concepts, which makes the system transparent and easier for clinicians to trust. Next, the role of the data visualization. Data visualization helped us understand how well our multimodal performed. Confusion matrix showed that the multimodal reduced false negatives compared to image only or audio only models. Accuracy comparison plots consistently showed higher accuracy for fused model. We also used feature distribution plots, which clearly showed separations between normal and pneumonia samples for features like contrast and spectral entropy. These visualizations were essential because They not only confirmed technical performance but also supported ethical goals like fairness, clarity, and interoperability. Moving to repeated actions, we responded to three main criticisms. The first is that multimodal systems that are too complex. While this is true, the improvements in accuracy and reliability, especially in a medical context, makes this complexity worthwhile. The second criticism is that the handcrafted features are outdated. Our response is that a healthcare interpretability is crucial and handcrafted features provide clear, clinically meaningful explanations that deep learning models cannot. The third criticism is that the audio and X-ray data can be noisy or inconsistent. Our multimodal design actually solves this problem because of the modality is noisy and the other can still provide reliable signals. This increases robustness and reduces diagnostic risks. Finally, the conclusion, our project demonstrates that combining X-ray features with lung sound features creates a strong and more discriminative systems from pneumonia detection. The CCA-based fusion significantly improves accuracy and reduced misclassification. Visual results supports these findings, and this explainability aspect strengthen the connection between model reasoning and clinical understanding. Overall, our framework is not only technically effective but also ethically aligned, transparent, and suitable for real-world medical use. Thank you.